All right, so we are talking today about measures of dispersion. So if we talked about measures of central tendency on Monday, right? What were the measures of central tendency? Mean, median, and mode. And they measured the center of our data distribution, right? Measured the center of our data distribution. And today what we're going to measure, or what we're going to talk about, everybody get a worksheet, by the way? Yes? All right, so what we're going to talk about is dispersion. So if Monday talked about where the center of our data was generally at, right, where the middle of our data, so to speak, was on average, we would call that a mean. The median is telling us where the middle of our data is, right, where half of the data is less than that middle, half of the data is greater than that middle. Now, I asked you to make sure that you tried to do the reading before you came to class. Okay, can somebody in your own words, and I don't expect you to maybe get it right, but try to get it down into something, right? Tell me what you think standard deviation is. It's a hard concept to understand, but can anybody try to put into words, what do you think standard deviation is? And it can't be the verbatim what I have it up there. Away from the mean? Okay, yeah, moving away from the mean. All right, I like that. Can we add to that? What else we might want to add to that? Moving away from the mean. What else? What does it mean to disperse?
Like separate?
Yeah, to separate, to spread out maybe, right? If I disperse chemicals, or if I had people that disperse, they would be spreading out, all right? And so with the standard deviation, it is a numerical value, right? It's a quantitative number for us to be able to say, how far is my data spread out away from the middle? Remember, the middle is our mean or our median, right? That's kind of the center of our data. And standard deviation is going to be a numerical value for us to be able to quantify and compare how far the data is spread out away from the middle. Now we have, when we talk about measures of dispersion, we have three things that we usually identify when we're thinking about dispersion. We have the range, okay? So range would have been the most basic way for us to talk about the spread in my data. It is simply the difference between the smallest value to the largest value, right? What's the range of values from the lowest number to the highest number? That is one quick way for us to talk about our dispersion. Another way would be standard deviation. And again, I'm going to show you what that means in just a second, but standard deviation would be that how far our data is away from the mean, the deviation away from the mean, and the variance. Now the variance, we typically use the mean and the standard deviation repeatedly till the end of the semester. We don't use variance as much, but the variance is just the square of the standard deviation. Does everybody know what it means to square something? Multiply it times itself, right? Okay, so 2 squared would be 4, right? 4 squared would be 16, because 4 times 4 would be 16, right? So when I square something, What I'm talking about here for the variance is I'm going to take the standard deviation and square it to get the variance. I can go backwards if we're thinking of the formula, and I can take the square root of the variance then to get the standard deviation. But let's kind of look at this idea of our standard deviation. Now, first of all, remember we're growing those variables, those symbols to represent our information that we're talking about. Standard deviation is represented by sigma, which looks like a cursive O. Remember I was telling you, maybe I told y'all that the some of our letters are going to be Greek and some of them are not. So sigma stands for the population's standard deviation. Sigma is the population's standard deviation, and lowercase s represents the sample standard deviation, okay? So sigma is the population's standard deviation, lowercase s is the sample standard deviation. And if I wanted to kind of represent what we're actually measuring here, I'm going to draw a line here. And I'm going to let that line represent the mean. What symbol do I use to represent the population mean? This is sigma. Mu is what I would represent. I don't know if that's what you said. Is that what you said?
No.
Okay. It was Greek though, right?
Yeah.
Yeah. All right. So mu, and what does that look like? A cursive U, right? So mu is this cursive U. Mu. What is the sample mean? The symbol is the sample mean. X bar, that's right. Okay. So X bar and mu represent the mean of my data. Okay? And we said yesterday or the other day, we said that the mean is the center of my data and standard deviation is the spread of the data. So let's just say that I have, and I'm just going to erase that for just a second. Let's say that I have all of these dots, and each of those dots represents a single data point. Okay? Just a single data point. So if I was taking maybe height, all right, the height of our class, the height of each person in here, then those points on my graph represent each one of y'all's heights. Okay? And if I were to take the average height, that is supposed to represent, you know, the somewhat of the median, the mean of our data, correct? So it would be the center, right? That's kind of what we said the other day. Now, if I were to come in here and I were to say measure the distance from that dot I just circled down to the mean, I would have a positive distance, right? Yes? Okay. Now I can come over here and I can measure this distance here up to the mean. I would have a negative, I would have a negative value, but the distance would still be there, right? Okay. I'd have a distance, I think is a better way to describe it. Here I can measure this distance, I can measure this distance, and so forth. Each time I'm measuring the distance that these data points are away from the center. All of that is just a measurement. I just circled them and I'm going to measure it. This is the way I used to have to do this a long time ago before we had cool computers that would do it for us. Okay. And what the standard deviation is all of these measurements right here. If I were to actually calculate those measurements that I have in there, and I were to add them together and take the average of those measurements, that's the standard deviation. The standard deviation is a single number, and it's the average distance my points are away from the middle. Okay? That's what the standard deviation is. It is an average distance, right? I'm going to, just like our mean is the average of all of our data points, the standard deviation is the average distance away from the middle that I have. okay? It's the average deviation away from the mean. That's what our standard deviation is. Now, if I have a bunch of points that are right around the mean, right? I have all of these data points that are centrally located right around my, let's call it horizontal line up there. I would not have very much distance away from them, would I? The smaller the standard deviation value, in other words, the closer it is to zero, if there's zero deviation away from the middle, we don't have any deviation, do we? There is no spread, okay? The larger the standard deviation value, the larger the number for standard deviation, the larger the spread is, the more spread out my data is away from the middle. The smaller the number, those values are concentrated right around the middle because there is no spread. The larger the standard deviation, the more spread out my data would be, okay? Questions? No? Does that make a little bit more sense? Yeah, okay. Now, we are going to go through the process. So y'all get your calculators out, help me do this, okay? We're going to go through the process of actually calculating the standard deviation of a data set by hand one time only. And you're going to go, okay, I can really appreciate technology after this, okay? Because it's a pretty labor-intensive formula process, I would say, for us to be able to do it. But I want to illustrate how it is that we come up with it before you actually start letting technology do it. So on your papers that I handed out to you, underneath that black bar, it says, is the exact same problem that I have up here. So you can follow along and fill it in with you on your paper that you have there. So I have data that represents the monthly cell phone bills for 6 randomly selected months, okay? So each of these values, these dollar amounts, represents the cell phone bill for 6 months. And what we want to do is we want to figure out what the standard deviation is for this information. Now, the first column that you have here on the left-hand side, this would be our data column, right? So each of those values underneath X sub I, right? X is a variable that's changing. X would be our data point that is changing. The I is just indicating that it would be incrementing, right? All right, so each of those values underneath that X sub I represents the data points from the list that we were originally given. Now, in order to come up with the standard deviation, I first need to figure out what X bar is for this data set. What again is X bar? It's the mean of the sample, right? It's the sample mean. All right, so the first thing we need to do is figure out what is the sample mean or the mean of this data set. And how do we find that again?
Add them all together.
Add them up, divide it by 6, right? I want you to do that. Add it up, divide it by 6. So we're going to go to 2 decimal places. All right, does everybody get $41.41? Okay, so I know that X bar, which is our mean of the sample, equal to 41.41. Now, if you're following along with our chart here, what I need to do is I am going to write X bar in every single cell here in this column. 41.41. all the way down. Okay, so I found the average, right? I found the center of this data set. The next process in this calculation for standard deviation says, okay, well, I need to know how far is each of those data points away from the middle. Remember the line that I drew you where I circled the data point and said I'm going to measure how far that distance is? Okay, so what we're going to do here is I'm going to take in this order. Remember, subtraction is not commutative. Order matters in subtraction. So what I'm going to do is I'm going to take my data point here in this column, and then I'm going to subtract from it 41, 41 for each of these 6 values. So when I take 35, 34 in my calculator minus 41, 41, I should get a value of negative 6.07. Did y'all get that? So I got a negative number. If I'm thinking distance is always positive, right? But that negative number is actually telling me that I am now below the mean, right? So it's almost a directional thing in essence, okay? It does have mathematical meaning, but we're going to actually do something to get rid of that negative number in a second. But that negative value is important because I want to know that I'm below the average. I might want to know if I'm above the average. Maybe I'm underestimating something or overestimating something. This is why that's important. So as you go through here, I'd like for you to fill in this next column. This column that we are working on is the deviation away from the mean. Right? It's that distance. All right. So once you get the distance calculated in that third column, now square it. Square each of those numbers. So for negative 6.07 squared, what do I get? Now I want everybody to make sure that on whatever calculator they are using, that they can get 36.84. Because a negative number squared should give you a positive value. A negative times a negative is a positive. Okay, and sometimes if you're using a calculator that you're not used to, entering something in there and squaring it without parentheses is going to produce the wrong answer. You want to make sure that you can get a positive 36.84. And if you can't, I'm here. I can help you with your calculator, whatever you're using. Okay. Is everybody able to get that? Do you need some help using your calculators? Because I need to know that everybody can get this. Once you have that done, the last step is to now add that column together. So I am going to add straight down the last column. So all these values here, straight down, I'm going to add them together. Okay? All right. What do we get when we add that straight down? One twelve point, I got 9.2. 112.9192, something like that. I don't remember what I had.
The third one from the bottom, I got 6.15.
Okay. I'll go with that. So we get somewhere around 112.9192, something like that, right? Yes? So when you're looking at this formula, what we did is we took the sum, which is represented by this capital E, looks like a cursive E sort of. Okay, that means to sum, the mathematical notation to sum, x sub I minus x bar and then square it, right? That's what we did. We took the mean, subtracted it from each data point, squared it, and then I added them all together. I just did it kind of in a grid over here. Now we're not done yet. See how this is a really, it takes a lot of work just to find the standard deviation. But what I now need to do is I'm going to come over here and I'm going to say, okay, the first thing that I'm going to do is I'm going to address our variance. And we're dealing with a sample here. And so I'm going to use the symbol S because the variance is the square of the standard deviation. So S squared, S is the standard deviation, variance would be squared. Okay, so that's where S squared comes from. And the variance can be found by taking this summation, the 112.91, and dividing it by one less than what we started with. So let's see, we had 1, 2, 3, 4, 5, 6. So that's why we're dividing it by 5. So we divide it by n minus 1. And when I do that, on your calculators, what value do you get? 22 point what? Move something. 22 point what? 58. That's the variance. That's the square. Okay, that's the variance, that's the square. Now the standard deviation is the square root of the variance. 22.58. So again, this is where you have to figure out how to find that value on your calculator. They're all a little bit different. What is the square root of 22.58? 4.75 is the number that we're shooting for. 4.75. That's a lot of work, isn't it? And by the time you're done with all of that, it's kind of hard to remember what was I even looking for, right? I did all of this work here, but let's remember what it is that we found. We found initially that the average cell phone price or the average phone price for this bill or for these people was $41.41, right? That was the average price of these 6 months with a standard deviation of $4.75. Okay, so that just tells you that that is the spread away from the middle. That's what the standard deviation says. It's the average spread away from the middle, because we know that we had cell phone bills that ranged as high as $7, almost $8 away from the middle. We had cell phone bills that ranged as close as 60, 70 cents away from the middle, right? So that 4.75 is that average distance away from the middle. That's the process that you have to go through to calculate it by hand. How many times do you want to do that? Right? And this was only a data set with 6 points in it, right? 6 points in it. So you can see that if I had to do this for something that was really, really large, it would be very taxing to be able to, to have to do this, which is why we don't do it other than technology. Technology is so available for us to find the standard deviation that it's just easier to do it that way. Now, I've calculated the standard deviation by taking the square root of the variance. If I gave you that the standard deviation was, say, 4, let's say I said the standard deviation that we found was 4, right? And I gave you a problem that said the standard deviation was 4. Could you tell me what this variance was? 16, right? It would be 16. I'm going to take the standard deviation and I will square it, right? That's how we find the variance. We're going to take that standard deviation and we would square it. Okay? Now, so we've got up here 2 values that are in green that represent our dispersion. We said we can find one of the measures of dispersion is variance. One of the measures of dispersion which we use most would be the standard deviation. But now how do I find out? I want to know what the range is of this data set. And how do you find it? So we need to come to our list of data points here, and we need to determine which is the smallest number, which happens to be what, 35, 34? I'm looking at that right? Is that the right number? All right, what's the largest value that we had in that set? 49.26. Take the difference in those two numbers. And you get 1392. That's the range. The range is just telling me that of this data set, I've got a difference between the very smallest number and the very largest number being $13.92, which would be a spread. Okay, so that's how you can find the range. So here I have the variance, the standard deviation, and the range done for me from StatCrunch. I will not ask you on a test to calculate the standard deviation by hand. Okay, this was our one time doing it, and we can all just be thankful that we have technology to do this from now on, right? Because we don't really want to do it. Lots of room for error there. However, you can find all of these values, the variance, the standard deviation, and the range from StatCrunch. Now remember, these values or these things that we're talking about, right? They are statistics. They are describing either the sample or the population, and therefore we find these values by going to that summary statistics tab in StatCrunch. I'll point it out to you in a minute, but remember where we found the mean, the median, and the mode in StatCrunch? Some of you have done your homework, some of you haven't, right? Wherever you find the mean, the median, and mode, you can also find the standard deviation, the variance, and the range. It's all right there, okay? You just pick out the pieces that you want, okay? Because it'll be at the same spot. And that's how you'll find those when you are using StatCrunch. All right, questions then on how I found that? Yes, sir?
The only question I have is I don't really understand how you get the, you said we were just doing this once or whatever, but why'd you divide 112.91 by 5? Why 5?
Because it's the degrees of freedom, and it is it's called the degrees of freedom. It's the sample size minus 1, which would be the degrees of freedom.
Okay.
And that's a whole other conversation.
Okay.
Part of the formula would be a better way to say it. Formula says n minus 1.
Okay.
Okay. All right. So if we're thinking about our paper that you're working on there, right? Somebody describe for me then. Somebody describe for me. I don't have it on. You've got a paper in front of you that says the range. Isn't that the first tab that you have on that handout that I handed you?
Yes.
What symbol, I didn't say this, but what symbol do you think we're gonna use for range? R. All right, capital R. Okay, capital R, that would be our symbol. That's our variable. How do I find the range? Subtract, it's the difference between the largest and the smallest value. That's right, okay? It's our easiest form of dispersion to measure. The easiest one, right? That was pretty simple, that to find the range. In fact, when you're doing this in grade school, right, that's one of the ones that they will do because you can subtract the largest from the smallest values, ordering a set and then subtracting them. Okay, how about the standard deviation? How about the standard deviation? What are the two symbols that we use for standard deviation?
Sigma and lowercase s.
Sigma, and which one is sigma for?
Sigma is for the population.
Population, and lowercase s is for the sample size, that's right. All right, and let me pull this up. Michael, let me see if I have it in here still. No. Let me write it in here. So the formulas, which you're not going to have to use, but I do want to show you this formula. Sigma is equal to the square root of the sum of x sub I minus mu squared divided by capital N, or sample standard deviation is square root of the sum of x sub I minus x bar squared over that n minus 1. Now, those are the formulas for standard deviation. And we did all of that, we just did it in different steps. Okay, order of operations tell us to work from the inside of something out, which is what we did. It took us a whole spreadsheet to figure out just the numerator right there, right? Okay, that was the sum of that last column. Okay, now the differences between these two formulas has to do with the population versus the sample. Notice that in the very first formula up here, which is sigma, we're talking about population. And now look at all of the variables that are in there. So population, I've got mu, which represents the mean of the population, and I have capital N, which represents the size of the population. So that formula right there is referring to the population, as opposed to the sample. And in the sample here, notice I have X bar, which is what we used because that's the mean of the sample size, or the mean of the sample. And then lowercase n, this is your degrees of freedom right here. Lowercase n represents the size of the sample, okay? Now, so I put those up there because it's important for us to understand something about standard deviation. What are we subtracting our distance from? What did we call this? The mean and the mean, right? What did we learn on Monday about means? They are easily influenced by what?
Numbers from like Bora, I forgot what they're called.
I heard numbers, that's all I can hear.
Like numbers separated from the group, like I forgot what they're called.
Okay, so want to help her out there? She's got numbers right. What else?
The way that they are distributed.
I don't know if I'm going to go with that one. I don't know if we can go a little bit further, if we can explain it. Mean, right? The mean. What was the NFL? What was the problem with looking at the NFL, the mean for the NFL players?
Oh, the highest one will have more influence.
Okay, so the mean was easily influenced by large or small values, right? easily influenced. We said it is not resistant to large or small values, right? Easily influenced. You remember this when we talked about it on Monday? Okay. So if the mean is easily influenced and swayed by these very large or very small values, do you think then that the standard deviation is also going to be easily influenced by these large numbers? Why? Because the mean's included in the formula, right? Because that's how we're calculating the standard deviation. So if the part of it that we're using to calculate the formula is easily moved by these large or small values, then the standard deviation is going to be equally moved by or influenced by very large or very small numbers. So the standard deviation is not resistant to outliers or large or small data. Okay, that's important. Make sure you have that written down. Just like the mean is easily influenced and not resistant, the standard deviation is easily influenced and not resistant. What was the measure that we used for the center that is resistant, that is not influenced by outside numbers? The median, right? The median was, and why is that? Because the median is just the middle number. The median has nothing to do with any other number around it except that it is in the middle of the list. So the median is resistant and the mean is not. Standard deviation is not resistant, and this is why, because if you look at the formula, you'll see that it is part of, the mean is part of the standard deviation. Okay, and then the variance. What variable would you be using for variance? Sorry, the what? Cursive O, sigma. Sigma what? Squared. All right. So variance says I'm going to take the standard deviation and I'm going to square it, right? So variance would simply be sigma squared or S squared. It's the square of the standard deviation. So we have the spread. We know how to now calculate, or we at least maybe are understanding, and we're going to practice on it a lot more because you have a test over this probably pretty soon. But we're going to be practicing what standard deviation means on our homework. Now, what we're going to talk about is the empirical rule. You need to make sure you have this copied down because you will be using this. Maybe you copied it down out of the notes that you read. That would have been a good thing too. But the empirical rule says, first of all, someone tell me what that shape is. How do we describe that shape? It's a bell shape. It's a normal curve, right? That's how we're going to kind of start considering it. It is bell-shaped and it's a normal curve. So what we're saying is that if we have data that falls in a normal curve, then we know how that data behaves. We'll call it that. Now, the empirical rule says, so all of the area in blue, everything under that curve would be considered area, okay? And they are a bunch of percentages, and all of those percentages added together add up to be 100%. So everything under the curve would be 100%. We know from the symbols that are at the bottom, right, at the bottom of the graph, that the very middle of our distribution, or the very middle of our graph, make sure you're putting those symbols down there as well, the very middle of our graph represents the mean. And this could be the mean of the sample or the mean of the population. Doesn't really matter, it's just gonna be the mean. The middle of our graph is the mean. We talked about that when we were talking about graphical displays. And if the middle of my graph is the mean, then what we're looking at from the empirical rule is how far away from the middle our data would normally occur. So what this says is, if you move to the right, and we also know that this display is symmetric. I'm gonna make it a little smaller so that I can move it up. Can you all on the back still see this? Okay. Remember, I can fold a symmetric graph in half. So what's on the left is equal to or is similar to what's on the right. So what this says is if I'm in the middle of the graph, if I move one standard deviation up from the mean, right? That's what sigma is. If I move one standard deviation above the mean, or if I move one standard deviation below the mean, 34% in either direction, 34% of the data that I collected would be right around there. So a total of 68% of the data that I've collected would be within one standard deviation of the mean, right? 68% of the data that I'm looking at would be right around the mean. And we look at standard deviation to find out how spread things are, how spread out things are. So in this particular case, within one standard deviation, we have 34 plus 34, or 68% of our data is going to be contained within one standard deviation of the mean. Now, if we move further out, notice as I keep going out, now I'm at 2 standard deviations away from the mean, either above or below. If I'm within 2 standard deviations of the mean, then I'm going to not only have the 2 34s, but I'm also going to have the 13.5 and the 13.5 on either side. That's a total of 95%. So what that says is if I have a data set that is normally distributed, I know from the empirical rule that 95% of the data that I collected is going to be within 2 standard deviations of the mean. What we're going to talk about is that's a way for us to determine how usual versus unusual it is for things to happen. If 95% of the time I got data back from around the mean, then that's something that, big deal. That happens all the time, right? Because 95% of the data that I collected happened right around there. If I'm outside of that, that's when we start saying, well, it might be unusual then for me to get a data point out here. So as we keep moving, so if I have 95% of the data happened in my set, if 95% of what I'm looking at occurred within 2 standard deviations, then think about that. I have 5% that doesn't get caught, right? Okay, we'll keep going on with the empirical rule. So now we're going to keep adding things up. Notice that we are now at 3 standard deviations away from the middle. 3 standard deviations, whether that's plus or minus, above or below. So within 3 standard deviations of the middle, we know on a normal distribution that that's going to encompass 99.7% of the data. Okay, 99.7% of the data. We expect 99.7% of our data to fall within that 3 standard deviations is what that's saying. We collect we know from the empirical rule how far we are from the center. Notice there's nothing else past that, right? I still have a little bit left, don't I? Right, I've got 0.3% or something like that left. That's like really unusual for us to have anything occurring way, way out there at the tails. So if you're more than 3 standard deviations away from the middle, then that's really not something that happens very often. We don't usually get data. Remember, we're thinking of a histogram. Picture this as a histogram. The tallest bars are where the most part of our data is occurring, isn't it? And as I move out to the tails, that's the smaller bars. There's less data in those bars. And so this is kind of what, that you put in those pieces together, right? The majority of our data is happening in the middle. In fact, if it's empirical rule, 68% of the data is gonna be around the middle. The farther out in the tails that you are, more than 4 standard deviations away from the middle you are, it's less likely to happen, right? Okay? This is how we can quantify our information, right? It's how we quantify the dispersion, in other words. Okay. Now, let's think about this. I'm just going to kind of overlay this with our sample that we were doing above for just a minute. And I'm going to need some help with your calculators. Above, we said that our cell phone bill had a mean of $41.41, right? Okay. And we know that the standard deviation was $4.75, correct? Okay. So this value here, if I'm thinking of a number line and kind of writing some of this stuff out, this number here, somebody tell me, what is 4141 plus 475? Okay, so that equals 4616. And now take 4141 and subtract 475. 3666. Now let's picture a number line here, right? We're picturing a number line, and I have a number line with a value of 3666. Okay, I have another number of 4141. I got another number, so I'm just making a number line, and they are evenly spaced by $4.75, right? That's the scale basically on it. What this says, using the empirical rule, is that 68% of my cell phone bills, right? 68% of my cell phone bills would fall between $36.66 and $46.16, because that is one standard deviation above and below the mean. You see what we're thinking there? Okay. Okay, and then we can keep adding that standard deviation to the mean, adding or subtracting it. So we're going to work a problem like that where we're applying the empirical rule in a minute. But that's basically what we're saying. Now notice that that empirical rule, what kind of shape was this? Normal or bell-shaped, okay? We're not saying that this works on a skewed data. It doesn't. It doesn't work for skewed data. It only works for normal data. It only works for bell-shaped data, okay? And therefore, which makes sense because the empirical rule is only talking about the mean and the standard deviation, skewed data, right? Skewed data is not appropriate. Let's see, I should say that a different way. Normal data is not appropriate, or the mean and the standard deviation are not appropriate for skewed data because it is easily influenced, isn't it? So we can only apply this empirical rule with these percentages to data that is not skewed, okay? Okay, and this is in addition to the problem that you have on your paper. So I want to work this one together, and then I'm going to let you work the next problem by yourself. You might want to add this to your notes. So this is our Brigham Young example, and it's a continuation, I would say, of the one that we used the other day in class.
It's not on our paper.
I know, it's not on your paper. You're gonna work this one just on a scratch sheet, all right? And then I have basically left this one on here for y'all to work. I just kind of added this example to do it for you. We'll do this one together, and then I'm gonna let you finish that one on your paper, so you have a chance to practice it by yourself. Okay, So what I have here is the Brigham Young example with the speeds. Remember, we calculated by hand the mean, the median, and the mode last week when we were in class, or on Monday when we were in class. Okay, well now, what I want to do is I want to know what the standard deviation is of this sample set. And I also, because I'm going to end up using the empirical rule, I also then want to go ahead and calculate the mean. I need those two things to be able to find to apply the empirical rule, the mean and the standard deviation. So my data set is here, it's in that leftmost column for speed. I'm going to go to stat, summary stats, and I choose column. Same thing we've been doing so far. Speed is listed in here already. This is where I'm going to come down here to the statistics, which are sort of here in the middle of my pop-up, and I'm going to choose the mean and the standard deviation. And I'll hit compute. So the mean and the standard deviation. So let's just write that down on our paper. We now know that the mean, we'll just use whole numbers here. The mean is 32, the standard deviation is 6. Because that'll make our numbers a little bit easier. Mean is 32, standard deviation is 6. That wasn't hard. We pushed some buttons into StatCrunch and that's how we got it. We don't have to calculate it by hand, okay? Now, because I eventually want to apply the empirical rule, let's pretend that we hadn't already looked at the histogram for this data, because I can only apply the empirical rule to data that is not skewed. So I would want to go in and I would want to quickly look at the histogram, and where the histogram is supposed to kind of convey a little bit of information for me, and I can just use a frequency graph. I think I had to change these to make it look better for us. And we can see based on that histogram, how would you describe this shape? It's bell-shaped or normal, right? It's not skewed. So we can apply the empirical rule, okay? This is kind of a check for us to be able to do that. So I now know that my data is applicable for what we want to look at. So in this question here, what I want to look at is, I want to estimate the percentage of speeds that are between 26 and 38 miles per hour. All right, I want to estimate what I think that would be. And the way that I approach this is, again, I'm using the empirical rule. And what I first need to do is I need to come in and I'm going to make kind of a number line that represents the bottom of that empirical rule that we were looking at. Okay, so I'm going to draw a line. And in the middle of that graph, I'm going to write the sample mean. And our sample mean was, what did we say it was, 32? Okay. And then to the right, I'm going to take my sample mean and I'm going to add the standard deviation. Standard deviation was 6, wasn't it? Okay. So that would be 32 plus 6 would be 38. And then I'm going to keep going. The next value is going to be X bar plus 2 times the standard deviation. So it would be 32 plus 12, or I could just add 6 more to 38, correct? Okay, so I would have 44. And then, just to be clear, this would be X bar plus 3 standard deviations, or in other words, 50. So just moving to the right, moving above the center, all I'm doing is I'm identifying where the center is, and I'm adding a standard deviation to it 3 times. Now let's move to the left. So to the left, I'm gonna subtract 1 standard deviation each time. And I should have values that would be 26, 20, and 14. Okay, so all I've done is make a number line, but this number line is very, very specific to the data set that I'm referring to, which is the Brigham Young data set, right? Talking about average speeds and standard deviations. Now I know that in the middle here, right, I know that this, so if the X bar is the center, that, I'm trying to think where I'm gonna put this. This value here is gonna be 32%, what is it, 34%? This value here is 34%. This value here would represent 13.5, 2.33. And then finally, it's 0.15. And those numbers are also on the other side as well. Now, the question says, I want to estimate what is the percentage of speeds that fall between 26 and 38 miles per hour. So I'm here at 26 all the way up to 38 miles per hour. Maybe a better way to look at that would be this way. If I were to add 34 and 34 together, that would be what?
68.
68%. So 68% of the speeds in this data set fell between 26 and 38 miles per hour. Okay, that's an estimate. Now I can actually go to the data set if I wanted to, and I could count up the number of speeds that actually occurred between 26 and 38, right? And I can find the percent of speeds that actually occurred in the data set. And I'm going to be very, very close. Now, the reason this says estimate is because it's a mathematical calculation, and that mathematical calculation doesn't always line up with exactly the real world, but it'll be close. It's enough for an estimation. Okay, let's look at I'll do it that way. So what if I wanted to say, what was the percentage of speeds that were 26 miles per hour or higher? Now I'm going 26 or higher.
You just add all of them together.
All right, add them all up. Tell me what you find. What's the estimated percent? Get your calculators out and add them together.
I got 83.98.
83.98, do we agree? All right. So we think it's 83.98%. So all we're doing is using a rule to be able to estimate those values. Okay, that's what the empirical rule is about. Now, how would I know whether or not the actual values, what the actual values were again? I would go to my actual data list and I would count up how many of them were over 26 miles an hour, count up however many there are and divide by the total. And that would give me the proportion or the percent, wouldn't it? Okay. All right. So you're going to have a practice problem like that if we get to it in a minute. But the last thing that I want to show you is going to be this right here. What we've looked at so far, and what we tend to find most of the time, is using like a full data set, right? Not data that's already been grouped, not data that's already been binned, right? Okay, and so you have the idea then that, well, how do I, if I'm given information that's already been summarized, how am I, and it's quantitative data, like what we're talking about, that's in groups of values, how would I be able to find the average if I don't know every single point in the data? Right? If I don't know every single point in the data, let me show you what I'm talking about here. This is an example. It says the data represents the high temperature distribution for the summer months in a city, for some city over the last 130 years. And so it's giving you the temperatures between the range of 50 to 59, 60 to 69, and so forth. And then the number of days that that city had that particular temperature. So for the last 130 years, this particular city only had 3 days with temperatures, high temperatures between 50 to 59. Do you see what we're talking about right there? Yes? Okay. So I took that data set. Remember, when you are, this is a homework problem or problem similar to your homework. Remember this little symbol over here on the side, right? If I click that symbol on the side, that's going to pull up the data set and let me copy it and open it in StatCrunch. Okay, so what I did is I took the data that you see right there for the temperatures and the days, and I copied it and I pasted it into StatCrunch. Now notice this data table right here, all 4 of those columns are what copied over. And that's what you're going to see copy over if you copy it yourself. All right. But I don't really need these 2 lower and upper limits in order to work on what I'm fixing to do. All right. So what I need to know is I need to have the categories, right? I need to have the bins right here. And then I need to have the frequency with which those occurred, right? There were 3 days that had temperatures in the range of 50 to 59. Now, if I want to find we'll just start with the mean. If I wanted to find the mean of a data set, tell me again what I do.
Add them all up.
Add them all up and I divide by the total number. The problem with grouped data is, of these, let's pick the 3 that I keep talking about, I don't really know what the actual value was, do I? I just know that I had 3 days that fell in the range between 50 and 59. So if I'm tasked with finding the average of these values, I'm kind of stuck because I don't know what the actual numbers are, right? I could add up 59 plus 59 plus 59, but maybe it was 50 plus 50 plus 50. I don't know. That's going to affect my average, isn't it? Because our average is easily influenced by our numbers. So how do I go about calculating the mean and therefore the standard deviation of grouped data? And there's a big formula for you to be able to look at and be impressed with the formula, but we're going to let technology do it. In essence, what it's doing is it's going to take the middle of that 50 to 59, okay? It's going to take that midpoint and it's going to multiply it times the frequency of the bar. And it's going to add them all together and then it's going to divide, okay? That's what it's going to do. But like I said, we're going to let technology do this for us. So when we're talking about finding the mean, the center, all of those things from grouped data, we're going to come to stat. You're writing this down. Summary stats, grouped binned data. Stats, summary stats, grouped binned data. Stats, summary stats, grouped and binned data. Now these commands to StatCrunch are always in the technology help part of your homework. All you have to do is click that button for help on it, okay, and choose the option for StatCrunch. So the bins, remember we have to have where those bins were located, and in this case it was those individual temperatures, right? The temperature ranges. So that's what it means by the bins. The counts would be the frequency that each of those temperature occurrences happen. So that was the days. Now choose consecutive lower limits. I don't know why, just do it. That's what they told us to do. Consecutive lower limits. And this is where I can come in and choose mean and standard deviation and click compute. So it's the same process as what we were doing before, but we're going to go to, if you've got group data, then you need to go to the grouped or the binned data option, okay? And it's going to work its magic on that formula, and it's going to give you the values that you have here. So we have a mean of 80.5. We have a standard deviation of 8. One standard deviation above the mean would put us at about what, 88 degrees? One standard deviation below the mean would put us at about what, 72 degrees? So 68% of the high temperatures recorded over 130 years, 68%, approximately 68% of the data reported for this city would have temperatures ranging between 72 and 88, if that's what I said. Right? 68%. You can keep going further and you can say, okay, well, 95% of the data that we collected is going to fall between these little bit larger ranges, right? That's what the empirical rule tells us is approximately what it is. The goal of this is for us to be able to say where the majority of the data is so that I can identify then if your data doesn't fall in the majority, then it's considered something outlying, something unusual, something to consider, something to look at again, okay? Now, there is no way for us to easily graph binned data. So from this, we just need to pay attention to the fact that the lower temperature range had a frequency of 3, right? Then I've got another, the next one successive would be 306, and the next one after that in the bins would be 1408, and then 1509, and then going back down to 394, and then finally ending at 10, right? So I have values that are increasing, they peak, and then they decrease, right? So that's what I'm going to look for. Remember, a table is simply, or a graph is simply the graphical representation, the pictorial representation of my table. And here, I have 4 graphs to pick from. You can see the temperatures are listed. It's a frequency graph. So I can take that column, those columns, right? The count columns, and I can just try to pick out which one of the graphs best represent my binned data. The third one that looks normal, right? Because I've got values over here on the vertical scale from 0 to the 1750. I know that from my information up there, I have a 3, a 306, 1408, 1509, and then I don't know what else is up there, but another number, right? It's coming back down, isn't it? So that would be the best representation. And there's no way for us to do that in StatCrunch. You just have to pull the information. You have to understand how to read a table and what the graph will look like. Okay? Are there questions on that? No? Well, we'll see. Okay. So what I want you to do is I would like for you to, and so the data set for your paper. M&Ms is up there. So you're going to use the data set that we have in StatCrunch, and you're going to work with some people that are around you. If one of you already has the StatCrunch pulled up or the internet already pulled up, that's a plus, and that way not everybody has to get on, only one person technically has to get on. But I would like you to turn around and work with the people around you, and you're going to work to answer question number 2, which is about M&Ms on your paper that I handed out to you, as well as we'll see how far we get. So at least we're going to try to see if we can answer some of these, okay? All right, start working on that. And again, the data set should be in your, in our And you're looking at the M&M weights. It's that column next to the speed column. But let me know if you don't see it for some reason. Is it showing up?
Well, I did the lower limits for determining the median. Yeah, like when you use the other limits, and the answer is actually really good. So when you talk about using, so,
The option when it's like choose lower limit.
yeah, so if you use just regular limits, you just. It's like. Yeah, okay.
0.05 versus 0.5. I don't know, and I forgot, I have to really study the formula.
Yeah, well, I just wanted to see how different it is.
It'll make a difference when you're trying to answer it on the homework.
Is that the 3.2?
Yes, ma'am.
Working on the homework or working on the
So we have about 12 minutes left. I want y'all to keep working on this. Ask questions while you can, but I do want you to make sure you bring this paper back with you when you come back to class on Monday so that we can finish off doing one of the activities. Did you join the group? So I'd like for y'all to be answering this with your neighbor, making sure, checking in that y'all are getting the answers right. That does mean that that's going to involve speaking to other people. So that generally means I would hear something going on in the classroom, right? So best way to learn statistics is to talk about it with somebody else.
Yeah, I got that too. Based off of that, why do you think the shape of the body?
And one other thing before so I don't forget before y'all leave, in case I forget to tell you, is so next Monday. Is it next Monday? See, we're Monday, Wednesday. Yeah, next Monday, you should expect to have a quiz over chapter 2. Okay, so if you didn't do very well on chapter 1, then maybe you need to think about what you're going to do, how are you going to study, maybe get some questions answered from me on concepts over chapter 2. We will not be using StatCrunch or anything, right? I'm going to just give you information and you'll have to, you'll just be interpreting the graphs that I'm already giving you in other words. Okay?
We don't have like a.
Not for the quiz. Not for a quiz, no.
So we're covering how many?
Just chapter 2. Chapter 2 is 2.1, 2.2, 2.3.
Roughly.